Okay, welcome back, everybody. So I want to ask a question because I'm a little bit torn about the homework and exam situation, because I don't like exams and I don't want to give you a ridiculously long homework 5. So how many of you would be terribly disappointed if I swapped out the final for a 6th homework? How many of you would think that was okay? Show of hands, how many would prefer to have a final? Okay. I wish there were more of you in here to vote. I'll decide soon, but I'm leaning strongly towards having a 6th homework instead of a final exam. So I think what I would probably do is write the final exam and give it to you, and you can do it like a homework. And if you want to take it in 2 hours to prepare for quals, that's fine. And then if you want to spend more time on it, that's also fine. Because I really want to ask questions that will be in next week's material on the exam or on the 6th homework. But I don't want to bury you with homework this week. Okay, and then last question. Would you rather have me split up the 6 homeworks with 80%, or would you rather the 6th homework be worth 20%? Split them up, even? Okay, all right, so I'll decide soon. On Monday, you'll know. I might ask you again. So if anyone has a huge objection, email me. Yeah. Okay, good. So today I'm excited. I want to teach you a lot of cool stuff about the Laplace transform. So last time we learned about the Laplace transform and how it's useful for solving ODEs. And this time I'm going to essentially build on this to talk about how you would solve ODEs with external forcing. So this is the basis of looking at system responses to vibrations, feedback control, a ton of very, very, very useful things. Okay, so I'm just going to give you the teaser of an extremely large and extremely important topic. And there's, I think, dozens of classes that go more into depth on what I'm about to tell you. Okay? Dozens of classes at the UW. Thousands of classes nationwide. Okay, so we're going to revisit the spring mass damper. And I brought a spring mass damper from my office, so no one try to call me. This is my spring mass damper, so we're going to do some demos. Except now what we're going to do is we're going to add an external forcing to our spring mass damper system. Okay, so I'm just going to rewrite what we have and kind of summarize the steps from the last lecture. Okay, we have a spring with spring constant K, a damper with damping rate C, and a mass with mass M. Okay, and we can write this down as x double dot plus some constant A. I don't know, some constant A. I guess I could literally call that constant C. X dot plus K x double dot. But now instead of looking at this equal to 0, I'm going to look at this equal to some external forcing. Did I mess up the signs? Yeah, just x, no double dots there. Okay, and instead of being equal to 0, we're going to have this equal to u of t, which is our external forcing term. So let's see if I can get some colors going here. And by external forcing, I mean this thing actually has units of acceleration or mass normalized force, right? Because it's equal to x double dot. So this thing has the same units as acceleration, or force, if you will. And you can imagine that maybe I have a piece of metal in here and a big electromagnet. And I can add some force to this thing. Okay? Okay, and maybe I also have some initial conditions. So for a concrete example, I'm just going to pick some numbers, and we're always going to be working with x double dot plus 5x dot plus 4x equals u of t because this thing factors nicely when you do the Laplace transform. And I'm also going to give it some initial conditions, x at time 0 and x dot at time 0 equals 2 and negative 5. And I just want to I'm just summarizing what we did last time. So I'm going to color code this also as orange. So my initial conditions are going to be in orange. Ooh, maybe not. My initial conditions are going to be red. Okay, and we're going to Laplace transform this, look at the solution, and then start breaking it down into pieces. Okay, so when we Laplace transform this equation, what did we get last time? What's the Laplace transform of the left-hand side? I'm going to Laplace transform some stuff. Laplace transform special, it gets curly brackets. S squared plus 5s plus 4 times x bar, my Laplace function. So it's really easy to read off the Laplace transform of this because every derivative is just another power of s. And I would also get some initial condition terms, and I could bring them all over to the right-hand side and say that that's equal to 2s plus 5. And also now I have my Laplace transform of forcing, plus u bar of s. So I went from the time domain into the frequency domain. Now, is everyone okay with me calling my Laplace transform the frequency domain? I go from time to frequencies s. S is just a generalized Fourier coefficient, so it could be I omega, in which case it's a pure tone frequency, or it could be lambda plus I omega, in which it's a frequency and a decay rate. Okay, and these terms, I'm going to keep track of them. I have my forcing term, and I also have my initial condition term. Okay. So what are the general, what's the general procedure for solving this system now that I have it in the Laplace domain? Okay, good. Get x bar isolated, so I divide by my characteristic polynomial, and then inverse Laplace transform. Maybe I do some partial fractions in the middle. Okay. Good. So I'm just going to go through all of the math one time, like we've already done this. So x bar of s is equal to my initial conditions divided by my characteristic polynomial, 2s plus 5 divided by s squared plus 5s plus 4, plus my forcing term times 1 over my characteristic polynomial. Okay, and I can break this up in partial fractions. We did that last time. It's just 1 over s plus 1 plus 1 over s plus 4. And the coefficients here are essentially my constant coefficients determined by my initial conditions, plus this function here times us. So this is just review at this point. And now if I want to inverse Laplace transform this, I say, okay, now I'm going to inverse Laplace transform, and I get x of t, my time domain function, which is what I really want, because we all live in the time domain. We don't live in the frequency domain. Or do we? I don't know. We might. So we inverse Laplace transform each of these terms separately, and they add because it's a linear operator. The Laplace transform is linear on these terms. So what's the inverse Laplace transform of 1 over s plus a? E to the minus at. And so here a is 1 and 4, so we have e to the minus 1 times time plus e to the minus 4 times time plus this thing, inverse Laplace transform, plus inverse Laplace transform of this whole forcing term. Now, what is the inverse Laplace transform of the product of two functions? The convolution of the inverse Laplace transforms of each of the terms. So I take the inverse Laplace transform of the first term, and I didn't ever prove that to you. I never proved that the inverse Laplace transform of a product is the convolution, but if you actually plug it in, it's super easy to show that it's the convolution. And you can Google this. A big believer of Google. The guy who basically programmed most of Google, at least early Google, gave a talk here yesterday, Jeff Dean. Have any of you heard of Jeff Dean? So he was the creator of MapReduce. He basically programmed the scalability of the Google algorithm so it could work on like millions of cores and humongous data. It's probably one of the most famous programmers in the world. He's been called the Chuck Norris of programming, not the Jeff Dean of programming. Not sure where this came from. Okay, so, but you can Google this, and Jeff Dean will tell you that the inverse Laplace transform of this product is the convolution of each of the inverse Laplace transforms of the two terms. Okay? And what's the inverse Laplace transform of u bar? U of t. Okay, so this one's super easy. Okay, so let's go back to the color coding here. We have our initial condition terms, and these are our initial condition response. If I had no forcing, then I would just have this initial condition response. Then in purple, I have my plus forcing term. So here's my plus forcing term, plus forcing term, plus forcing term. So if I had 0 initial conditions, I would just have the purple terms. Okay, and the last thing we need to do is figure out how to inverse Laplace transform this function, right? If we can do this, we have everything else. Make sense? Okay, so how might I go about doing this? How would I go about inverse Laplace transforming that nasty 1 over a quadratic function of second order polynomial in S? Yeah, we do partial fractions, right? We just do partial fractions, and now it's like a different initial condition response where this is the term we're trying to solve for. Okay? So let's just do a simplification. Let's for now assume we have no initial conditions. So assume 0 ICs, and this is just for simplicity. Then our function x of t is equal to the inverse Laplace transform of 1 over s squared plus 5s plus 4 convolution with u, my function u of t, my forcing function. Okay, so we want to find this inverse Laplace transform, and we're going to do this using partial fractions. So let's just do that really quickly. And before I do this, I want to just write down something. So essentially, what this is a statement of, this is in time domain, this is the solution to my system with forcing. In the frequency domain, x bar of s is just equal to this function times u bar of s. And so what I can do is I can take x bar of s divided by u bar of s, and I can say that that's equal to this function 1 over s squared plus 5s plus 4. And I'm going to give this really special function a name. I'm going to call it the transfer function. So we're going to call this g of s. We're going to box it. And we're going to give this a name. We're going to call this the transfer function. And I call it the transfer function because it tells me, essentially, if I have some input u, this function tells me how much output x I get for this amount of input u. Okay, so this is the transfer function from u to x. And we're going to look a lot more at this transfer function and what its properties are. So I just want to tell you that this thing has a name. This thing we're about to inverse Laplace transform is called the transfer function. Okay? And it's essentially 1 over my system dynamics. It's 1 over my characteristic polynomial in S. It's given completely by the coefficients of my ODE. Okay, so to compute this inverse Laplace transform, we essentially do partial fractions. So we say we have 1 over S squared plus 5S plus 4. And how do I do partial fractions?
Factor it.
I factor it. I just say this is A over S plus 1 plus B over S plus 4. And I cross multiply, and I get something like A plus B times S plus 4A plus B divided by my denominator. And so to equate the A and B that satisfy this are the A and B that make the numerator equal to 1. Okay, so my numerator has to be 1, which means all of my S terms, A plus B has to be 0. Okay, so B equals minus A. And then this term, 4A minus A, has to equal 1. So 3A equals 1, which means A equals 1/3, and B equals minus 1/3. Super simple, partial fractions, okay? So this transfer function G of S is equal to 1/3 times 1 over S plus 1 minus 1/3 times 1 over S plus 4. So what's the inverse Laplace transform of my fancy transfer function? We know how to do each of these inverse Laplace transforms. They're easy. So this is 1/3 e to the minus t minus 1/3 e to the minus 4t. Okay, so it's super simple now to compute this inverse Laplace transform of my transfer function. And the last step is I have to convolve that solution with my input function u. That's the only thing I have to do now. Okay, so the last step now, I'll actually just write it out explicitly, I guess. So we have our particular solution, our homogeneous solution with no forcing. And then we have this convolution, which is an integral from, let's say, 1/3 of an integral from minus infinity to infinity of that function, which is e to the minus t minus e to the minus 4t. These should be taus, times my function u of t minus tau, d tau. Okay. I just pulled the 1/3 out because I didn't like it being inside the integral. It was bugging me. Okay, so we have now we have a full solution to this ODE with forcing, right? We started with our initial system x double dot plus 5x dot plus 4x equals u of t. We Laplace transformed both sides. We isolated x bar in terms of our initial conditions and our forcing function. We essentially did partial fractions on both of these terms and simplified. And then we inverse Laplace transformed, and we got our homogeneous solution plus this convolution integral, which is our forcing term. And it's essentially convolving our forcing u with the dynamics of our ODE, e to the minus tau and e to the minus 4 tau. Okay, this is a good time to stop and ask for questions. Yeah?
So can we do the convolution also for the inverse Laplace transform?
What do you
that
mean?
part? The convolution for that part, for the 1 over s squared plus 5x.
Yeah, that's a really good point. So this is, 1 over s squared plus 5s plus 4 is really equal to 1 over s plus 1 times 1 over s plus 4. So it stands to reason that if I inverse Laplace transform this, this is, L inverse of this thing equals e to the minus t convolution with e to the minus 4t. Is that what you mean? And I think that must be true. And I must get something like this with a 1/3 popping out. Yep. Okay.
Do we want the bounds of the convolution integral from minus infinity to t, or?
No, I really mean from minus infinity to infinity. So my t is right here.
Okay.
So conversely, I could have had t minus tau, and this could have been d tau. Like this could have been tau. You can switch which of the terms has the t minus tau and the tau. It's no problem. This bound, though, is, so you're asking a really good question. In practice, this bound might be from 0 minus to infinity. It might be just before 0 to infinity, because I'm kind of assuming that nothing was happening before time 0. Time 0 is the beginning of the universe as far as I'm concerned, and I don't care what was happening before that. Yeah, so oftentimes I'll replace this with like 0 minus, which just means just before 0. Yeah?
Why does Laplace get curly brackets?
4a used to get curly brackets, and I just was slipping. But Laplace, it's just as nice to, I'm always doing this of some function of another variable, and so I don't like having too many round brackets.
Mathematical convention, or is it just your...
No, not really. If I had thought a little more, I would have done it for Fourier transforms too. Like usually you do it for Fourier also. Okay. So we can do this all in Matlab, which is what I'm going to show you. This whole thing you can do in Matlab. Not exactly sure. Let's see. Yeah, okay, good. I'll show you this in Matlab. Okay, other questions first. So what are some U functions that I might want to try? Sines and cosines. Maybe I force my system sinusoidally. I just give it some input that's a sine wave. Good. What's another one?
Impulse.
Impulse. Maybe I hit my system with a hammer. Another function. Delta function is an impulse. Yeah, so that's the hammer.
A step function?
A step function would be good. So let's say that I just turn on my control at time 0 and I keep it on forever. I turn the lights on. Step input. Those are some functions I might want to do. And fortunately, each of those functions has a relatively simple form that I can actually do this convolution integral. So in the homework 5 that will be posted by the end of the day, you're going to be solving these types of ODEs, and you're actually going to be by hand solving this convolution integral for particular U's, like a step function or a delta function or a sine or a cosine. And for example, if this U is a step function, it's super easy because it's just 1 from 0 to infinity. So you just multiply this by 1. Easy. Okay? Delta functions are also easy, but you'll get some experience actually solving this convolution integral by hand for some particular U's. Even better ways to solve this is not to do it using this convolution integral. Maybe I won't have you solve it by hand because it's kind of stupid. The better thing to do would be to solve this in the frequency domain. So I have essentially my system, my solution x in the frequency domain is my transfer function g of s times the Laplace transform of my input function u. Okay? So another thing you're going to do on the homework is you're going to show that if u of t is a delta function, then u of s is 1. That's super nice. I multiply my transfer function by 1, and I inverse Laplace transform it. Convolution with nothing. Okay? If my u of t is a step function at time 0, this is the Heaviside function. It goes from 0 to 1. Then my u of s is just 1 over s. So I take g of s, my transfer function, times 1 over s. I get a third order polynomial on the bottom. I literally get 1 over s times s squared plus 5s plus 4. I can factor this denominator into 3 partial fractions, and I can inverse Laplace transform each of those. So this one, super simple to solve without using convolution. Okay? So for lots of common u's that I like to use, like impulses and steps, I can actually simplify the system in the frequency domain and then inverse Laplace transform the product. And I don't have to think about convolution, because I don't like thinking about convolution. It's a little convoluted. Okay, so you're in the homework, you're going to by hand show that the Laplace transform of this is this. That's easy, it's just an integral. And then you're going to use those properties to solve systems by solving them in the Laplace domain and inverse Laplace transforming. Okay, I'm going to show you how to do some of this in Matlab before I go any further. Okay, again, this is a tremendous field. That is used in lots and lots and lots of other classes, and I'm just giving you kind of the faintest intuition about what we're doing here. Okay, so clear all, close all, CLC. Does anyone remember what CLC does? Clears your command window. Okay, so let's just put some comments here. So my ODE is the second derivative of x plus d times dot x plus k times x equals u of t. I'm just going to use d for damping, k for spring. It's easy. And what I'm going to do is I'm going to say S equals a transfer function. So in Matlab, there's this really slick command called TF, and it makes a transfer function. And so this is how I initialize my Laplace variable S. So in Matlab, I'm going to be able to do symbolic stuff in terms of this Laplace variable, because I'm creating a transfer function, which is just S, my Laplace variable. Okay. Then what I'm going to do is I'm going to say my system equals 1 divided by, I should probably pick a d and a k. What was my d? 5? K was 4? Okay. So I'm going to have my system be 1 divided by s squared plus 5s plus 4. I'm going to save this as test Laplace. And I'm going to run it first of all. So nothing went wrong. And if I uncomment this, you see my Matlab window telling me that I have a system, 1 over s squared plus 5s plus 4, and it's a continuous time transfer function. This is built into the student version of Matlab. It's in the controls toolbox. Okay, so I have my transfer function. And in Matlab, I can do really slick things, like I can take the impulse response of my transfer function. And that's the impulse response of my transfer function. So if I gave this thing a delta function at time 0 in the input, this is what the position of my spring mass system would do. It would rise and then decay back to where it was. Okay? I'm going to show you mathematically how to derive this. I can also do things like look at the step response. So if I step my system, if I just take my initial force and I increase my force to some value like 1, then the position of my spring mass system just goes up to some steady state value, and it has some transient motion. Yeah?
Both of these are assuming 0 initial conditions.
Both of these are assuming 0 initial conditions. I can give my system an initial condition response using the initial command, but I never do, so I don't know how to use it. I guess it's easy. Initial system x naught. So if I wanted to give this an initial condition, I could do that also. Okay, so it's really easy to define these transfer functions in Matlab, and it's also easy to get basic information that I want out of the system. So let's do something a little simple, a little more interesting. So what we're going to do is we're going to change the damping rate. And let's pick a spring constant k equals 1. So for d equals 0.1 in increments of 0.1 to 2. So I'm going to change my damping rate from very lightly damped to pretty heavily damped in increments of 0.1. For each of these d's, I'm going to recreate my system. I'm going to say sys equals 1 divided by s squared plus d times s plus k. And then what I'm going to do is I'm going to look at the step of my system. I'm going to look at the step response of my system. I'll pause for dramatic pause. And I will hold my graph so that we can see them building up over time. Any questions about what we're doing? I have my system. It's parameterized by d and k. And so in Matlab, I can go through and just do this for a bunch of d's and a bunch of k's. So I'm going to do this for a bunch of damping rates. And hopefully this will work. And I will plot the system as it becomes more and more damped. Color scheme's kind of awful, but you can see that for low D, I have big oscillations. Maybe I'll not hold on. Maybe I'll hold off. You see it becomes less and less damped, and eventually becomes like critically damped. Sorry, it becomes more and more damped until it becomes critically damped. Does that make sense? Okay, let's also do the same thing, but let's change the spring constant. Okay, so now D is going to be 1. I just have some damping for k equals 0.1 to 0.1 to 2. So now my spring constant is becoming stiffer and stiffer. Same thing, system equals, I can just copy all of this. Now as my spring becomes stiffer and stiffer, then my effective damping becomes less and less, and it becomes more springy, right? It becomes more, it oscillates more when I make my spring stiffer, even for constant damping. Which is why we introduce these new parameters, zeta and omega sometimes, because k and damping are kind of bad parameters. They're not independent, really. Okay, lots of cool stuff you can do in Matlab, super simple using transfer functions. Okay, questions, more questions about the Matlab before I go back to the board? Yeah.
Something as changing like u of s is equal, or u of t is a sine wave
Sure.
without doing the Laplace transform?
Yeah, so that's called LSIM. Doc LSIM, this just means linear simulation. And so I'm going to do LSIM of my system with some input vector u and some time vector t. So let's do that. Let's say that let's say t equals 0.1 in increments of 0.1 to 10 to 100. And let's say that u equals sine of t. And let's say that my output is equal to LSIM of my system, comma u, comma t. I think that's how I do it. And then I'm going to plot t by the output. Maybe I'll call this x, because my system is x. Okay, so this is my system response to a sinusoidal input. There's some transient, but eventually it also, the output looks sinusoidal. And that makes sense, right? If I take my spring mass system and I start sinusoidally forcing it, there's some transient, but eventually the output also starts looking sinusoidal. And it has the same frequency as the sinusoidal input that I'm giving it. Okay, this is a perfect segue into the next part of what I was going to tell you about, which is the frequency response to sinusoidal inputs. Okay, so a little bit more MATLAB, or a little more math, and then a little bit more MATLAB. So this function g of s is extremely important. This transfer function g of s tells me essentially everything about my ODE. It tells me how my ODE will handle initial conditions. It tells me how my ODE will handle external forcing. And there's lots of powerful and useful things I can do in the frequency domain with this transfer function. And there's entire fields dedicated to understanding this transfer function and how to manipulate it and plot it and do all kinds of things with it. Okay, so let's say that our transfer function is called g of s, and we have no initial conditions. So we're going to look a little bit more at our transfer function g of s, this thing here. Okay, so for linear systems, like all of the systems we've been looking at, linear partial differential equations, linear ordinary differential equations, if I give my system a sinusoidal input, then I get a sinusoidal output at the same frequency, but with a different magnitude and some different phase. Does that make sense? I force the system with the sinusoid. I get a sinusoid out, but it might have a different phase. It might be a cosinusoid, and it has a different amplitude. So the idea here is that I have my transfer function g of s. This is my physical system. And let's say I give it some sine omega t as the input. U of t equals sine omega t is my input to my system. And the output, x of t, is going to be the same frequency sine, but it's going to have a new amplitude and some phase. This is always true for linear systems. So this is for linear systems. This is always true. At least in the steady state. There might be some transients, but this will happen for, like, once the systems reach steady state and the transients have died out. Okay, so this A is the magnitude, and this phi is the phase. And so the idea is that we can get the magnitude and the phase of what our system does to sinusoidal inputs by looking at this transfer function. This transfer function is going to tell us how our system handles inputs of different frequencies and what the magnitude and phase of the outputs will be for those given frequencies. So basically, I have A as a function of omega, and I have phi as a function of omega, and I want to know what these functions are, because this tells me a lot of information about how my system responds. Okay, and the way we do this is we say, essentially, the magnitude and phase of output to a sinusoidal input is given by, can be solved by the transfer function. So it's given by the transfer function evaluated at that frequency. So evaluated at s equals I omega. So I literally take g of I omega, right? My transfer function is a function of my Laplace variable s. S is a complex number, so I can take g of I omega. This is sines and cosines at frequency omega. And this is a complex number. I mean, just verify. Plug in I omega into that transfer function, you get a complex number, right? It's a complex function. And so what we have is that we can look at the magnitude of g I omega. Just what is the raw magnitude of this complex number? That's A. That's my amplitude. And phi is essentially the angle of this complex number. So just how do I find the angle of a complex number? What is angle of A plus BI? It's the arctangent of B over A. Okay, it's just what is the, like literally in the complex plane, I have A plus BI. What is this angle? It's arctangent of B over A. So that's what angle means. It's what is the phase angle. So the phase is the phase angle of my transfer function at I omega. Okay? And the great thing is that these are both functions of omega. I can do this for all omega. I can do this for really, really low frequencies. I can do this for really, really high frequencies. And I can do this for all frequencies in between. And I get numbers A of omega and phi of omega. I get my amplitude and my phase for any input frequency omega that you like. And I can plot these as a function of omega. So this is called the frequency response, or the bode plot. There was a great engineer named Bode. I almost named my dog Bode, but I don't think it's a great dog name. And you can draw the Bode plot for your system. So I'll just draw the Bode plot for the spring mass system and then explain what it means. Up here, we're going to have the magnitude of GI omega. And down here, we're going to have the phase of GI omega. And for our system, what we have is it stays constant for a while, and then it starts to drop off. And my phase starts out at 0. And then at some point, it starts to go down to minus 180. Omega and amplitude are on a log scale. Angle is just in degrees. It's not on a log scale. Okay, so I want to tell you what this means physically with my spring mass system. So this is actually for my spring mass system. Now, would you say that this is highly damped or lightly damped? Lightly damped. There's not a lot of friction. It's just a coil. It's a coil. So because my system's lightly damped, I'm probably actually going to have more of a peak here. I'll explain this peak. And I will also probably drop down in phase more rapidly. This is something you'll learn about in control theory. But let's start thinking about what we mean physically, how we physically read this frequency response. Shit. Maybe I should have a different example that doesn't tangle. Okay, so the idea is, let's say that I start forcing this system at a really, really low frequency. Really low frequency. What this tells me is that my magnitude is going to be basically 1. This is 1. And it's going to be in phase with my motion. So let's do this really slowly. Really slow sinusoid. And the position of my mass is tracking my position at the exact same amplitude. This isn't stretching or contracting. Okay, so that's unit magnitude. And this is at some, there's some frequency below which the phone perfectly tracks the input forcing. Perfectly. Unit magnitude, 0 phase. Now, at some frequency, there's a resonance, so I give it a little bit of force, and I can get this thing to basically jump around. This is a tiny displacement, and the phone's jumping, and it's at about 90 degrees out of phase. So it's a little hard to see that from this example, but if my hand's doing a sine, the phone is doing a cosine. Maybe a minus cosine. It's doing something cosinusoidal. And then finally, what we find, and this increase here in magnitude means that I'm actually getting more motion out of my phone than I'm putting in. Right? It's an increase in my amplitude out. And finally, at very, very high frequencies, what this is predicting is that the magnitude of the phone motion actually becomes very, very small, and it becomes out of phase with my hand motion. So this one's a little harder for me to do. But if I move this thing really, really, really fast, shit, it starts flipping because it's a coil, not a spring. But if I move it really, really, really fast, you can see that this phone is actually not going up and down very quickly. Like it's actually not going up and down at all. If my hand's moving unit 1, then this phone might be moving like 1 centimeter. And its motion is going to be exactly out of phase. So when my hand moves up, it's going to move down. And then when my hand moves down, it's going to move up. Right? So it's completely out of phase. I don't like this phone very much. Okay, does that basically make sense in terms of how to read this frequency response, this bode plot? And it's really easy to evaluate the frequency response using my transfer function. I have a function of s, and I can plug numbers into that, and I can find out what the magnitude and the phase of the complex numbers are that come out. Okay, let's do this in Matlab. I have a few more minutes. Okay. So basically, the first thing I'm going to do is I'm going to change the damping rate like I did, but instead of plotting the step response, I'm going to plot the bode plot. And now I am going to hold on. So bode is the command in Matlab that does this frequency response. It's named after bode. And we can see our bode plot as I increase the amount of damping. So imagine I made that coil stiffer and stiffer and stiffer. So it was more and more, and not stiffer. I increased the damping, so I made it more and more and more damped. You see that I initially had this big resonant peak, which means that if I give it a little forcing at the resonant frequency, then the output amplifies. But as I increase the damping, my resonant peak is damped. That's what damping means, right? I damp my resonant peak. And I also, for higher resonant peaks, my phase change happens much more rapidly. I can do the same thing if I change my spring constant instead. So now as I change my spring constant, so I make this thing stiffer and stiffer, you see that now if I give this thing order 1 input, the output response gets smaller and smaller. And the frequency where resonance occurs gets higher and higher. Right? As I increase the stiffness, the resonant frequency gets higher. We know this. Omega naught, right, is the square root of k over something. And it gets higher and higher when k goes up. And you can, this is a great engineering diagram because you can literally tell exactly what your system's going to do at any frequency by reading 2 numbers off of this plot. It's great. And as we know from linear systems, Fourier transforms and Laplace transforms are linear. So any signal I make, even a step function, I can break up into a sum of sines and cosines. And so I can look at how different frequency components of my step will either be amplified or decay. And some of my step might have a resonance, and so that frequency might oscillate a little bit in my step response. And we'll look at this a little bit more. Okay, I'm basically out of time. I think I will probably continue a little bit more in this vein on Monday, do a little bit more analysis on these frequency responses and the Laplace transform and what it means. Any questions about what we've done before in the last minute or two? Okay, I owe you a homework. It'll be out later today. So sometime before midnight, there will be a homework. All right, thank you.